Welcome again. In the last classes, we have covered through the sample preparation by focused ion beam. We have done the basics, instrumentation, and we learned about the ion beam column, gas injection system, manipulator, and how to draw patterns by and how this fib is function to sputter the material from the sample, correct, the sputtering process. So we have gone to little bit basics related to sputtering process also, and some uh, uh, methods which is used to either prepare the TM samples or the APT samples, or any of the sputtering related things. Fine. Now, in the next few sessions, maybe 3 or 4 sessions, what we do is uh, we will show you how to load the sample in focused ion beam, how to prepare the atom probe samples. Step by step, we'll approach, and this will be demonstrated by my students. Is Saurav and also Shashi. Both of them, they will teach you how to prepare the sample before loading into the chamber, and what are the protocols to be used during the preparation, and also the parameters which are very important during preparation of the samples, right? So I hope that you will go through all of these videos, and it will be helpful for in future for how in sample preparation.
So in this video, I am going to explain the sample loading procedure in dual beam secondary electron ion SEM microscopy, scanning electron microscopy. So this is the holder. This is called quick loader holder. So I will explain you later the what is the quick loader it is. So in this holder we can mounted our sample. So we can use two different set of sample. This is the cold mounted sample which is wrapped with the aluminum foil, and another is the without mounted sample. So this is the without mounted sample. It is a electropolished sample. So both the sample we can use for the preparation for APT sample. So now first what we will do, so we use the carbon tape because carbon tape is a conductive in nature. So this is a carbon tape from where we can cut a small piece. So yeah, we can cut a small piece of carbon tape and we paste it on the holder. Fine, pasted, and we cut another piece. And after pasting the carbon tape, we can mount our sample. Now I stick the sample with the carbon tape. So first we have to check that sample should not fall. Okay. And the next step is to check the my sample height should be proper. Then it can go inside the load loader, quick load loader. So we have some demo holder where we can check that our sample is going or not. So our sample height such that it should not be higher than this circumference of this quick loader holder. Now I remove my sample. Now my sample is fine and I am going to load the main microscopic quick loader. This is a Helios dual beam FIB machine which is consists of two different type of beam. One is electron beam and another is ion beam. So first I will explain the electron beam. So it is a electron beam column. The top part is the source electron beam source, which is thermionic source or fake source. Here we have a fake source, field emission. After the source, we have a condenser lens system, which is consist of condenser lens, aperture. We have a objective lens system, and we have a scanning coil. So this is the part basically in the E-beam, normal SEM column. Next is you can see, so this is the cable which is connected to our to our electron beam source. This is a high tension cable, that white one. So this is a BAC detector. Okay. So this is a backscatter electron detector for the imaging purpose. So already I mentioned this is a E-beam column, and now this is the I-beam column. So this is from I-beam. You can there is a gallium source is there. So that gallium source basically we will use for ion beam imaging. Now this is a GIS needle. Whatever platinum we use for the deposition purpose, welding purpose, we use the GIS needle. So this is a GIS needle thing, and this is the manipulator things. This is the micro manipulator which is used to lift out the sample. This is the quick loader rod. This is a special type of rod. We don't need to vent our entire chamber. So only this portion we can vent and we can load our sample. So once I will press the venting button, so it will vent this small chamber. First I vent the chamber and open the lid. Now next is I place the sample at this position. The next thing is, so this holder, you can see there is a two hinges is there. Now we can push sample little backside, and the hinges should fit at the middle of this gap of the holder. Once you move the sample backside, so that hinges should be at the middle of this holder, the gap of this holder. Now we have to lock these things. So for the locking this the sample with the holder, we have to turn it to the right side. Now the sample is locked with the holder. Now you have to close this holder lid, and now my sample is ready to go inside the microscope chamber. Next step is to press the pump button. Once you press the pump button, so our chamber basically will start to vent. So vent and pump button both are similar in this machine. So now our chamber is venting. Now my sample is already locked with our quick loader holder. Now it's ready to insert inside the microscope chamber. So before inserting, we have to vent the chamber. So before venting means we have to press the pump button. Already we mentioned before. So that pump button and the vent button both are similar. Now our microscope chamber actually has started venting. So it will take around 1 minute to vent the chamber. After venting, we will load the sample inside our microscope chamber. Now my chamber has vented. Now we use this button and this lock to open the gate, and we apply some force, some pressure to allow the rod to go inside, and it will go till the end and then unlock it, and it will come back again the same position.
Now you can see the microscope software interface, which is divided into four segments. The top left segment, which is gray in color, which is basically a electron beam window. Top right, which is black in color, it's called I-beam window. Bottom left is napcam, and thus you can see the bottom right is basically a side view of the microscope. Now basically now I am doing the napcam. So napcam is basically taking the picture of our sample. So now it's taking the picture, taking a photo of our sample, and it will take at least 10 to 15 seconds to take picture. Now you can see that it already taken, and next step is to double click on my sample. So you can see my sample actually wrapped with aluminum foil. Now I double clicking it, and once I double click, now my sample is perfectly aligned with respect to electron beam. Now the next step is to turn on the electron beam, and turn on is both the beam, and next step is to set the stigmator and beam shift to 00. The main idea behind this, to whatever the previous user used in that stigmator and beam shift, so you make it 00 to make it perfect condition. Now the next step is to unpause the electron beam window, Now once we unpause the electron beam window, you can see our sample. So now you have to magnify it, and next step is to focusing. Now I am doing focusing on my sample, and this is the some dust particle. So it easy to focus on a dust particle initially. So you have to do focusing at very high magnification, around 10,000, 12,000 x magnification, and you have to correct astigmatism as well. Now next step is to link Z. How much distance my sample is from the pole piece. So now I am same thing. I am doing astigmatism correction, astigmatism correction, and once I link Z and make it set to 4. So 4 is basically the eccentric height for this Helios microscope. So it may be different for the different microscope. Now I make the NavCam window is turn into an electron beam window. Now in that NavCam window, I will actually insert BAC detector, ABS detector, annular backscatter detector, backscatter electron detector. Now you can see the features. So in AC images, my feature is not clearly visible, but in backscatter, it is a jet contrast imaging. So you can see nicely that two different features, two alternate lamellar plate. The sample is basically a titanium aluminide sample. The titanium aluminide is consist of two alternate plate of Ti3Al and TiAl, and this is that now in that window I am basically doing focusing at backscattered mode. Now focusing going on, I am doing focusing. Yeah, now I am correcting astigmatism as well. So it actually basically takes little bit time to perfectly focusing and perfectly to correct astigmatism. So once it done this thing, once actually our region of interest, if now yeah, so basically we first we have to do select our region of interest. Now our region of interest is fixed. The next step is to draw a pattern. So okay, basically actually I chose a wrong pattern. Yeah, so now you can see I have, this is actually my region of interest, that green color rectangle box. From this, that green color rectangle, that box, this is the this is our region of interest. From this region basically we will lift out sample for our APT needle. So in this mm, APT lamella, we actually cover both the phases. So we'll try to do to cover that both the phase should come in a tip, that we can identify the what solute element is going which phases. Yeah, now I turn on the E-beam window in secondary electron mode, and I go to view and do center crossing to locate to easily locate my feature. Yeah, that same position I'm same pattern I am actually doing in AC mode. Yeah, now the next step is to insert the platinum needle. So first we have to pause this electron beam window. Next, yeah, I'm going to pattern option, and actually I insert the GIS needle, that gas injection system needle. So next in application, I choose platinum E deposition surface. Always choose surface. Not there is so many options is there, surface structure, and I make dimension X around 8 micron, Y 0.5, Z around 0.5, and now you can see this is there is so many options is there in application. Now I set it surface, and scan direction you can choose anything. Here I choose top to bottom. Now I started patterning. It will take around 1 to 2 minutes. So it's showing this is, it will take around 1.5 minutes. 1 minute 50 seconds it will take. So meantime I can tell that how this thing happening. Basically this is that gas injection system, this platinum, that platinum precursor is there. So with that precursor is consist of trimethyl platinum molecules. So when that trimethyl platinum molecules comes to our sample surface, when a high energy electron beam strike, it basically that precursor gas, that trimethyl platinum is basically decomposed, and the platinum atom actually deposit on our sample surface. So this is the actually basic mechanism by way in this way that platinum actually deposit on our sample. The platinum basically used to prevent our sample from a gallium damage. The main purpose of the platinum deposition is to prevent sample from the gallium damage. So the sample, so my professor already mentioned that aluminium, magnesium, those sample are very sensitive in gallium. So in this kind of sample, we need to deposit platinum more to prevent the damage from gallium. Now you can see our sample platinum is nicely deposited on the surface, and you can see in E-beam window in AC electron by secondary electron microgram that rectangle, same type of whatever pattern we put, same type of platinum actually deposited on the surface. And the next step is to do eccentric. So first, what is eccentric? Now you can see that once I tilted my sample, my features actually moved from center to bottom. So I using the Z height stage movement by stage movement, and I actually increase the Z actually. So bring my sample at the center. So this process is called eccentric. So I will explain what is eccentric is. So eccentric is basically, so at a particular objective lens current value at particular Z position where our region of interest will not move during tilting. So basically this is a eccentric. So at the eccentric point, or is eccentric height, our electron beam and the I beam meet at the same point. So now I tilt at 30 degree to check. Now it's little bit move. So again I use this Z height and bring to the center. And next I go to up to 52 degree, because in 52 degree my ion beam column is perpendicular to my sample. Now again I align adjust the Z height by stage movement. And now my eccentric is done. Now I go to the 0 degree, and now you can see that my features is almost at the center. This little bit changing, but it's almost center. So this position you can, so 3.88 mm is basically a eccentric height now. Initially we actually set at 4, but 4 is not is not a eccentric position. So 3.8 is now is eccentric now. So now again I have to tilt 22 degree. Now for APT sample preparation, we generally tilt our sample 22 degree. Now you can see the features is nicely visible in E-beam. And now I set now I go to I-beam window, and always you can see that blue mark is there in that blue mark actually indicate that you are in that window. That window is basically in live mode. So that blue color represent below this. So now I go to ion beam window, and now I set the current at 9.3. So 9.3 basically high current we basically generally use for trenching purpose. So initially, now I set we will do trenching from around 1.5 micron above from our region of interest. Now I can make I put a rectangle box which is 3 micron, and we will do trenching 1.5 micron above and 1.5 micron below. So initially I will do I'll do trenching at the top part. So dimension x is around 12, y is around 5, and z is 6. Put, and always that scan direction towards the sample from top to bottom. So now I set pattern perfect position, and I can start this patterning. So basically gallium ion actually remove material from this pattern region. So it will take at least 2 minutes. Now you can see in E-beam window. So my material is basically removing. So the high energy gallium ion basically sputtering atom. So trenching is now going on, and our region of interest at the middle. So now focused ion beam microscopy has some inert gas sources like xenon that will basically help for this aluminum sample preparation, those who are those material which is more sensitive to gallium. So we have this FIB source is called plasma FIB. So here we don't have plasma FIB, but it's the plasma FIB is very good for sample which are sensitive to gallium ion. So this high energy actually gallium basically sometimes it damage sample too much, but normally that nickel based super alloy, titanium alloy, it's fine. Now almost it's trench. I think 20-second is left. Yeah, around 20-second. Almost it trenched the top part. Now we take that snapshot, and yeah, one thing I want to mention in I-beam window, don't unpause it at a high beam current, because if you unpause it, that high energy gallium ion actually damage your region of interest. So this is the main thing. So don't unpause it at a high current. You can unpause it at a low current, but don't unpause high current. Now I go to 0 degree. I come back to 0 degree, and I am doing a little bit of focusing. Next step is to rotate my stage to 180 degree. After rotation, you will see that top part will come to the bottom. The top trench part will come to the bottom. Now my features actually move, so I will use stage movement. Now we can see it is below, and now you can see that top trench part actually basically comes to the bottom. Now I'll do a little bit of focusing. Again, I have to tilt my sample to 22 degree. Yeah, it is eccentric is disturbed little bit. Then again we make eccentric little bit and bring our region of interest at the center. Yeah. So once it's center, we turn on. We go to the high beam window, and you can see now it is in blue condition below. It means it is in light mode, and same rectangle pattern we will put at the top. Yeah. Same dimension, application scan direction is top to bottom, and we'll start the trenching process. Now you can see in e-beam window that is now trenching at the top, and already you can see the bottom is already trenched because now this is 180 rotated. Now the top part is now trenching. Same the high energy gallium ion removing material. And it takes the same time, around 1 to 2 minutes. So the time is actually basically depends on the current value. So if you use some basically high current, then it will take less time. If you uh, use low current, then it will take more time. So always if you want to do trenching, you can use the high current. But one thing you have to check that in I-beam column, you don't unpause it at high current value. Now it's trenching. Uh, it's 40 seconds is left. Yeah, it's removing. And another thing, so you in always you in during trenching, you ISPI is basically you keep you can see at below there is a ISPI time interval. So after 5 seconds, it is basically taking images one. So always keep ISPI as low because you have to see the trenching procedure. So always you have to monitor that it should not cut our region of interest. This is the main thing. Now I am doing tilting 45 degree to check that it cut perfectly from both the side. Yeah. So I am using the beam shift. So using the beam shift and bring my region of interest at the center, and you can see that the sharp line is there, so it cut from the both the side. Can check at 52 degree as well. So it cut perfectly. Now I will come back to a 0 degree. Now you can see in E-beam window that in both the side it cut perfectly. So trenching part is done. Now next step is to cut at the left side. So we basically in cut in left side to bring our manipulator for lift out sample. So next I will draw some rectangle pattern at the left side, and the dimension is around x is around 3 or 4, and y should be entire height of this thing around 8 to 10, and z is around 6, and it's that pattern should be from left to right scan direction towards the sample always. So now it's started. Now you can see that that left part of our sample is basically removing. So the main idea behind this, so we will can insert the manipulator easily, otherwise our manipulator actually touch. So the main idea behind to this trenching, this process to insert our manipulator. Now it's almost cut. Yeah, you can see in I-beam window as well by snapshot. So you can take snapshot to check. Always you have to check. Have to take snapshot after few, time interval 3-4 seconds during cutting. And now I cut little bit at top part for the safety purpose, that it should not be attached at below or anywhere. It can easily move, freely move. Okay, now I change the current. Now I change current from 9.3 amps to 7 picoampere. Now this is the very low current. Now this current is fine for unpause my I-beam window. Now I insert the manipulator. Now you can see in the E-beam window our manipulator is there. That white color is basically our micro manipulator. Now in E-beam window we are basically align the XY. So in E-beam window you can see the XY movement. You can align XY. So I am using this XY movement and align my manipulator with our sample, and my manipulator and my sample should align perfectly. You can see in E-beam window it aligned perfectly. Now I am going downwards, so using this jet. So basically I am going down, and now once it's reached almost near to the sample, so it's best to insert the platinum needle. Now I am inserting the platinum needle to weld my sample with the manipulator. Again, now the once you come very near to the sample, so you can decrease the step size. Now it is this step size is around 500 nanometer, you can see, and slowly you have to move, and once you see the once it touch the sample, at that time you have to stop it. So you can see E-beam window, it's almost touch, and I-beam also you can see it almost touch. Yeah, now I change the current value. Yeah, sorry. First, I'll draw some pattern. Same rectangle pattern. Now we'll make a bond of platinum with our sample, and now I change the current from 7 picoampere to 80 picoampere. So basically at 7 picoampere, it's very difficult. It will take long time to weld. So that's why we increase the current little bit. Now the Z we put around 2 micron and XY is basically zero 0.8 and 2. So now that platinum deposition is going on. Now it's making bond with this micro manipulator and our sample. So you have to take a snapshot in between to check that it's how bonding happening. It's bonding or not. The welding, yeah, bonding or welding or not. Yeah, yeah, it's bonding actually. The welding, the deposition is going. Yeah, it's nicely deposited. You can see. So once this deposition done, then we will cut from the left side. Then we can easily remove our lamella from sample. We will use the high current for cutting purpose. So same 9.3 nanoamps current I use for cut sample. Yeah, same start patterning and it's cutting. You can see it will take few seconds to cut. Once it cut, you can see. Yeah, now I change the current. Now you can see it cut nicely. And I unpause the window, I-beam window. Yeah, there is some, it is attached. That's why I cut little bit. Yeah, yeah, now it's cut perfectly. So sometimes you feel during when you try to lift out, you feel it attached. So then you have to cut it. So now it's perfectly free and it will come out. Yeah, it's coming. Yes, coming. Initially, you have to make small step like 400 nanometer, and after removing 3-4 times, you have to do small step. Then you can increase the step size. Now 10 micron. After that, you can retract the manipulator. You can see it almost coming from sample. Yeah, you can see that. Now you can retract our platinum GIS needle, and also you can retract the micro manipulator. Now the one part is over, that lift out part.
So same removing time of the sample. So you have to press the same pump button. That pump button actually vent my chamber. So it will take at least 30 seconds to 1 minute to vent the chamber. Once the chamber vented, so we use this rod, quick loader rod, to go towards the at this stage and turn to the left and go and move forward, and again we have to turn right to lock the sample and it will come back again. So now my sample actually come back from the microscope chamber to this small the venting box chamber, quick loader chamber. Now I press the venting button for vent this chamber, open the lid, and here that this rod we turn towards the left. to unlock sample. Now I take sample from the microscope. So after removing sample from the microscope, now we have to remove the sample from the holder. You just remove it by your hand. You just apply some pressure, it will come out from the holder. We have to remove the carbon tape